Chapter 13, Landing Gear and Braking Systems. All right, now for this chapter, the landing gear and braking systems enable safe ground operations, including taxiing, which is rolling the aircraft on the pathway before getting to the runway. The taxiway is the inner runways that are not made for or designed for takeoff. Then takeoff, landing, and rejected or aborted takeoff scenarios. These systems must absorb high impact loads, provide directional control like steering on the ground, and ensure reliable stopping performance under a wide range of operating conditions, meaning that the braking system should be highly performant and work very intensely, even when you have severe conditions like an emergency landing with no flaps and with a high load of fuel still being carried on board. Okay, so they need to perform almost an immediate or short stopping, okay, without overshooting the runway, guaranteeing the safety of the landing in such case. Landing gear types and configurations. Functions of the landing gear. The primary functions of the landing gear system are to support the aircraft weight on the ground, absorb landing and taxi shock loads like a damper. So you have a damper to absorb these shocks, just like the wheel of a car. Provide the braking and directional control. Again, directional control is, in other words, steering. Okay, because the aircraft, in order to turn left or right, it needs to be steered via the wheels themselves as long as it is on the ground, okay, before it gets to the takeoff runway. And also, finally, enable retraction to reduce aerodynamic drag in order to increase the efficiency of the flight and reduce the drag. Retraction meaning that like the wheels need to be pulled back up, okay, and housed or sealed within their housing compartments. To the right here, we see an illustration of the landing gear. So you have down lock and drag brace, okay, which is the lock when the gears are extended so that they won't budge during landing, okay. Metering pin extension, okay, rotation lock pins, yeah, after braces, oleo cylinder, okay, many parts here, axle beam assembly, sensing wheel, okay, you have sensors also on the inside, tires and wheels, these are four tires here, brake assembly, that is part of the braking system, axle beam fold and compensating actuator, which by the way, as the wheels run, they generate power, okay, that would be sensed like read as a signal that the landing is, that there's a touchdown. So when you have a rolling of the wheels, this would work like an actuator, okay, an alternator, I'm sorry, generating a signal. That signal would be read by the computer system and interpreted as a touchdown that is successful, okay, that the landing gear has touched the ground, and which would enable the RTO, like the auto brake system, to fire off, okay. And here you have the retraction actuators, which would be fed by an electrical power, and actuators again convert from an electrical energy here in this case to a mechanical energy to retract back the wheels to like pull them back to their housing, okay, during the flight. And so you have rotation actuators, okay. Landing gear configurations. You have tricycle landing gear, the most common configuration in modern aircraft, consisting of two main gears and a nose gear. Advantages include good ground stability and improved pilot visibility. Okay, You have tail wheel, which is conventional landing gear, consists of two main wheels and a tail wheel. More common in older or lighter aircrafts, but less stable during ground operations. And this is where, when the aircraft lands, it would be in a nose up position, which has the drawback that the pilot would have a hard time seeing the ground. Okay, but it wouldn't be that serious here in such case because the aircraft is not as large as the ones such as the Boeing 737 types and larger. That's where you would need a lower pitch during landing so that the pilot can see the runway. And multi-bogey landing gear used in large transport aircraft to distribute weight over multiple wheels, reducing pavement loading. The ground pressure in such case would be W divided by A, where W is aircraft weight and A is the total tire contact, total tire area, but not the area exactly of the tires, but the area of contact between the tire and the tires in total and the ground. So that would be the part of the tire that is actually touching and in direct contact with the terrain. Shock absorption. Most aircraft use oleo-pneumatic shock struts combining compressed gas as a damper solution and hydraulic fluid. Energy absorbed during landing. This is how you evaluate it, okay? Because you have speed of landing, which would be descent speed, and the mass of the aircraft. So the energy that would be generated is a kinetic energy equal to 1/2 mv squared. M is the mass of the aircraft and v is the velocity of the touchdown. Strut force approximation would be F equal PA, pressure multiplied by the area of contact. Retraction and extension systems. Actuation methods. Okay, so the landing gear extension and retraction may be accomplished using hydraulic systems. This is the most common, okay, through the hydraulic power being transferred via pipes. Using electric motor driven systems, okay, like actuators that would receive an electrical power then converted into a mechanical power, or pneumatic systems, which is, has a limited use. Okay, hydraulic retraction systems. Starting from that, okay, hydraulic actuators extend and retract the landing gear using system pressure. As we've mentioned before, the actuator force would be F equal pressure times cross-sectional area. The actuator speed is given by V equal Q divided by A, where Q is the volumetric flow, which is the velocity multiplied by the cross-sectional area where the flow of the fluid is taking place, okay? Or through which the fluid is flowing with that streamline velocity, okay? With that circulation velocity. Uplocks and downlocks. Mechanical locks secure the gear in the up or down position, preventing it from budging or from retracting by mistake, for example, if it was extended, or extending falling down and dropping and extending by mistake if it was retracted, especially during mid-flight. Downlocks are critical for landing safety and are often gravity assisted. Okay, they are assisted with gravity. So as the aircraft lays its own weight on the terrain, on the runway, that very same weight driven by gravity is what locks the landing gear in place. Okay? Emergency extension. Now, in the event of hydraulic failure, emergency extension methods include gravity free fall systems. This is when you have an emergency landing and there are no hydraulics that are necessary to drive the extension of the landing gear. So in such case, you would extend the landing gear using the gravity free fall system. okay? Like you would release it from the lock, from the up lock, to extend on its own weight. You have another choice would be manual hand pumps, okay, in other types of aircraft, and blow down systems using compressed gas in order to push the landing gear in place, okay, forcefully. The potential energy which aids this free fall would be EP equal mgh, which is the mass of the landing gear times g, the gravitational acceleration, times h, which is like the height of the gear from its extended position. Now I want to revisit the necessity for having locks, whether an up lock or down lock, for a landing gear system. So why do we need the locks to begin with? At first, the landing gear is so much heavy in weight. Once it is extended, it is subject to massive aerodynamic loads. That's why we need a guarantee that it won't budge. It won't retract by mistake, and it would be fixated, like it would be stable during the landing. Okay, it won't like collapse by due to the aircraft's weight. Okay, now more than that, keep in mind that the hydraulic system is not fail safe. Okay, is not completely not reliable the word, but you cannot guarantee it fully. Okay, it has the possibility to fail, so you need something that would lock the landing gear to ensure, okay, to make sure that it would stay in place during the landing. That's why we need the both systems, you know, the uplocks and downlocks. For the uplocks, what you have is like a spring driven roller that will enter in place, okay, like a hook. When you have the landing gear retracted, that will guarantee that it won't drop on its own weight, okay? Actually, during emergency landing, where you know the hydraulic system fails, which is, by the way, this is what releases the landing gear. It would be the hydraulic system disengaging this hook, okay, turning it in order to allow the gear to be retracted via the hydraulic pressure. When you have a failure, you need to allow the gear to drop on its own weight through the force of gravity, and you have a safety button that would release the hook, allowing, you know, the gear to be retracted again by the force of gravity. As for the down lock, when you extend the gear for the purpose of landing, you have another hook that will go in place. Actually, it is a like a side brace that will go ahead of the landing gear on purpose, and this side brace, once the gravity pulls down the aircraft, actually this side brace would be pushed like yeah, the landing gear would have the tendency to go back in a straight formation. However, the gravity would itself, it's a very intelligent trick, the gravity itself would be pulling that brace sideways in order to like guarantee that the landing gear would always remain fixed, okay, in the same position. So it would push it outward. Meanwhile, this strut, like this brace, was having the tendency to push it inward, okay, landing gear. So once the aircraft lands, the gravity itself would push this brace outward to guarantee the landing gear having like a straight standing on the runway without any possibility for it to retract by mistake. Brake systems and anti-skid. Okay, wheel brake systems. Modern aircraft use multi-disc hydraulic brakes located in the main landing gear wheels. The braking force required would be FB, or force for braking, is equal to mu multiplied by N. Mu is the coefficient of friction, and N would be the normal force, okay, exerted by the rotating wheels, like the gear wheels, against the wheel itself to allow it to brake, just like the brake of your own car. The braking torque is T equal the braking force multiplied by R. R would be the radius of the wheel, of course. Kinetic energy dissipation during landing or rejected takeoff, brakes convert kinetic energy into heat. This is how they actually stop. Okay, so EK or kinetic energy is equal to 1/2 m, the mass of the aircraft, multiplied by v squared. V is the velocity of the aircraft. Now, I might have made a mistake, which wasn't like a mistake, but it was not accurate when I mentioned in previous slides when I said that the velocity is actually the descent speed. No, it is actually the both the vertical and horizontal velocity. It is the velocity vector altogether. Okay, it's not the vertical or horizontal component alone. Okay, mostly the horizontal it would be. Okay, now it's actually divided into horizontal and vertical components, the sum of which would give you the velocity. So the brake temperature rise is given by delta T. Okay, the rise of temperature is equal to EK divided by MB CP. CP is the calorific capacity. Okay, heat capacity, and MB is the mass of the brake. Anti-skid systems. Anti-skid systems prevent wheel lock-up by modulating brake pressure. Okay, so this is how they work. So they prevent wheel lock-up by modulating the brake pressure, meaning the brake pressure would be converted into a current, and this is what would be used. All right. So wheel slip ratio is lambda equal to velocity of the aircraft minus the velocity of the wheel divided by the velocity of the aircraft. Optimal braking occurs at a specific slip ratio, typically 10 to 20. Okay, the autobrake systems. Autobrake systems automatically apply braking after touchdown to achieve a selected deceleration rate. A equal delta V over delta T, or dV over dt. The acceleration is actually the derivative of the velocity in respect of time. Now again, the slip ratio, how is it measured? It is equal to V aircraft minus the velocity of the wheel divided by V aircraft. But how do we get these values? You see, the velocity of the aircraft is given by the airspeed or the ground speed. Okay, the ground speed during the landing, it would be more accurate. The velocity of the wheel can actually be detected by the alternator that is connected to the wheel. So as the wheel rotates, it would generate a current, and by detecting or measuring the frequency of this current, you can evaluate or calculate the velocity of the wheel. Okay, so we subtracted from the velocity of the aircraft divided by the V aircraft. That would give you the slip ratio. Okay. Gear position and warning systems. Landing gear indication. Cockpit indicators show the status of the landing gear. So if you have green lights, it means that the gear is down and locked. Red or amber lights, it means that the gear is either unsafe, which is it did not lock properly, or in transit. Now, you have different types of sensors to get that type of information. Okay, so the gear position is sensed using proximity switches, limit switches, and WOW or weight on wheels sensors. So what is the difference between these three types of sensors and how do they actually work? If we start with proximity switches, these are the switches that do not detect the position of the landing gear via a direct contact, but instead they are like detectors of proximity. So when it's retracted, if it's in proximity of the sensor through the measurement of the inductance or sending a signal and receiving a return signal like a sonar, so to speak, or like a perimeter detection. This is how it senses the position of the gear. Now, for the limit switches, unlike the proximity switches, they work in direct contact. So when the landing gear is locked upwardly, so if it's retracted and locked, once it's locked, it comes in contact with the switch that would fire a signal to the cockpit that it is up and locked. Otherwise, if it's locked down, so that would be the uplock. If it's locked down, also it would be in direct contact with a switch to indicate that it is extended and locked. For weight on wheels or WOW sensors, they work through strut compression or decompression. So, and it is a very completely almost different mode than the operational mode of the proximity or limit switches. So when the landing gear is fully extended and on the ground, it would be compressed, the strut would be compressed. Meanwhile, when the landing gear is retracted, it would be decompressed. Warning systems, oral or visual warnings alert the crew of unsafe configurations. Okay, so you have, for example, unsafe landing condition when throttle is low and gear not down. Brake and tire monitoring. You have modern aircraft include brake temperature monitoring system or BTMS, so which considers the operation normal as long as the temperature of the brake is less than or equal to the maximum allowed temperature. Because as you know, that the heat is used as a way to slow down the aircraft by converting the kinetic energy into heat, okay, during touchdown. And as long as the temperature is acceptable, okay, the airplane remains under safe conditions. Now, the tire pressure monitoring ensures structural integrity. So the pressure of the tire should be like it is equal to F divided by A, which is the area of contact between the wheel or the tire and the ground. Okay, so the temperature of the brake again should be evaluated via like the RDS, okay, RDS resistance system, so as to detect whenever the temperature becomes overheated in a dangerous way. Actually, this once has caused a fire on board and downed a DC-9, I think, in Saudi Arabia, okay, many years ago. It was around 1984, something like that, okay? I don't, 1986, yeah, around that period of time, okay? And the entire fire was caused by the overheating of the landing gear, okay? That had its own rubber ripped off, okay? Because it needed a change and it wasn't changed on that day. So that compromise lit the entire aircraft on fire. Summary: landing gear and braking systems integrate structural, hydraulic, and electronic subsystems to ensure safe ground operations, effective stopping performance, and reliable crew awareness through indication systems and warning systems.